So this is my virtual apartment, and this is the robot cleaning my virtual apartment. He needs to go everywhere and clean all of the tiles. And this is him doing this cleaning at the beginning, so without having learned anything. And as you can see, the robot is more or less randomly driving across the apartment like any good cleaning robot would do, right? But let's wait a while until it has finished learning. And this is the same robot after it has completed training. Not only will it clean all the tiles, but it will also do it in the most efficient way possible without wasting any moves. I am a big fan of reinforcement learning. Today we will implement an algorithm which is able to learn. It is an adaptation of so-called Q-learning. And Q-learning is a very reliable reinforcement learning algorithm. Reinforcement learning means that your agent or the robot is able to learn just from the environment. So it will get rewards for good action and it will probably get negative rewards for bad actions. And using these rewards, it will update its policy and get better over time. The best thing about it is that we will implement everything from scratch without using any libraries, just for the GUI a little bit. So you will be able to learn a lot today. So this includes also the system's representation, how the map is laid out, the learning algorithm itself, and also the surrounding driver and GUI code. So during the implementation, I will explain you a little bit the certain design choices behind it and also dive into the algorithms that allow all of this to work. Feel free to skip to the part in the chapters below, whatever interests you most. So let's get started. The first thing we need is a representation of our world or of our system, of our state, however you want to call it. All of that, what we will do today, is based on a map. So the map is what you saw in the layout of the robot. It's basically here, this thing here on the right side. This is the map that we need to implement. And this map basically has a size in the X direction and a size in the Y direction. And it also has a const expression array, which is saying whether some of the cells are occupied or some of the cells are free. So for instance, here you see that all the red cells and green cells, the robot can go, and everything else in between the robot is not able to go. So this is the representation of our map. Using this map, we can use it as a template parameter for our roombot state. This means that the roombot state is distinct for each and every map that you can give it. So from a design perspective, this is good because you can easily change the map to a different map just by changing here the template parameter of your state. The state itself is implemented pretty straightforward, which means that it knows where the current robot is. So it knows the X and Y position of your robot, and it also knows the state of the tiles that are in the map. So you see we have also a tiles array that consists of size Y and size X tile states, and a tile can either be clean or it can be dirty. So if it's dirty, it will be red in the visualization later, and if it's clean, it will be green. Then we need the constructor for our state, and our state itself will be constructed with all of the tiles that are in the state. They will be dirty, except the first tile on the top left, which is always clean because the robot is also starting on this tile, and it can never be on a dirty tile because it would immediately clean it. Because we want later to store our roombot state in something like a map, something like an array, something like an STL container, it does make sense to implement an operator for comparison, just because then the STL algorithms all can work on that. Usually you do this by implementing the operator as a friend, and here we have a friend operator for the roombot state, the left hand side and the right hand side, and we do just a simple equal comparison, so which means that we look whether all of the tiles are equal, and whether all of the robot positions are equal, and if that's true, we just return true for that case. The next thing is that we need to know which actions our robot can do in which state. So for instance, if we are here in this tile of our map, the robot can go either to the right or it can go to the bottom, but it cannot go to the top and it cannot go to the left, because then it would leave the map and it would leave our state in some undefined value. In order to do that, we go to our state, so this roombot state again, and we can retrieve actions. And the actions, they are defined in a separate class, and these are really straightforward. So we have a direction which the robot can go. It's left, right, up, down. And the roombot action just has this direction as a member and can be printed. And then it also has some sort of a Q value, which I will explain a little bit in detail later on. And we're able to print whatever action has been chosen. So this is just for debugging purpose, that we also can print these enum values. And now we need to retrieve the set of possible actions given a certain state. So which means that we will return those actions as an unordered set. That's also why this one here needs to be hashable. And in order for that to be hashable, we specialize here the standard hash function. So to give you a little bit of an overview of the unordered containers in the STL, the unordered containers in STL, like unordered set or unordered map, they require for user implemented types a specialization of the standard hash function. So the container needs to know how this type here can be hashed. And we need to tell it by defining this standard hash function. So we implement here the standard hash function for this particular template parameter roombot action. And we just say that as a hash result, we just use the size t cast of the direction itself. Because it's a enum with 4 values, it's not really impressive, the hash itself, and it will never collide, which is a good thing in this case. So in order to store now these actions and the set of all the possible actions, we need to know, given our current position of our robot and given the map that our robot is operating in, whether it can go to the left, whether it can go to the right, whether it can go up, or whether it can go down. And if this is the case, so if the map at this position is valid, then we will add this action here. We will create an action and we will add this action to the set of possible actions for that particular state. And after that, we will return that set. And this is now limiting the action space of our robot, because later on we will query for those actions and only execute the actions which are actually allowed. The next thing that we want to have is something like a reward function. As I have said, the learning is based on rewards, and we need to know how good a specific state is, also in comparison to how the previous state was. So usually we will define some reward function based on a previous state, and because it's inside our current state, we can then compare what has changed and say whether it was good or bad. In this case, we will introduce a reward that is always negative, -1, because the robot made a move and we want him to be as efficient as possible, which means that less moves are better than more moves. And then we just compare whether the previous state had less clean tiles than the current state, and if this is the case, every tile that has been cleaned, it will receive just a single 1 reward for it. After that comes some debug functionality, so we can query for how many tiles are dirty or how many tiles are clean, just to allow some debugging, and we can also print it. Because we also want to store this in a map, usually we need to specialize the standard hash also for our roombot state, and here we do the same as we also already did for the actions. But in this case, we use a little bit of a more complicated hash function, which we just use the position and also all of the tiles as a bit set basically. So if a tile is clean, then we have a 0. If it's not clean, if it's dirty, then we have a 1 or something like that. Just to have every single state represented by a single hash value. Now putting this all together in the complete system roombot, which has the states and the actions, and it also has an update function which allows us, given a certain state and given a certain action, to determine what state will be the next state. So we see that if we have the direction left as an action, then we decrement the x position. If we have right, we increment the x position, and so on and so forth. And if we are at the specific position, the tile state will be changed to clean regardless of what it was previously. We are also able to reset it. This is useful for the learning later on. And that's basically it. We have defined our complete system. We have a map, we have the roombot, and the roombot has a state and it has actions. And based on those states and the actions, we also know how to proceed in time. So let's dive deeper into how Q-learning works. Q-learning is a learning algorithm which usually employs something that is called a Q-table or a Q-matrix. And a Q-matrix has the following things inside. So it lists usually all of the states that your system can have. So for instance, this is a particular state, this is a particular state, and so on. And then for each of the actions that you can do in that state, it lists a particular value. And this value is called the Q value, and it represents the future reward basically if this action would be chosen in a particular state. So for instance, we have here the starting state of our robot, which is the robot is in the top left corner, and this state will now be somewhere in this table. So we will use this state to look up in the table the Q values for the particular actions that we have. So for instance, in this state, we are either allowed to go down or we are allowed to go right. We are not allowed to go up and we are not allowed to go left, because these actions would mean that we leave the map. Now, in order for our agent to work, we basically use whatever Q value is the highest. So if our actor needs to decide where it wants to go, we just say that if Q down, for instance, is bigger than Q right, we will choose Q down, and that's it. That's already how our actor chooses the best move possible. Then usually in learning, we have something that is called an epsilon greedy strategy, which means that we don't always follow the best move possible. We will, for some random amount of times, choose any option that is available. This allows our actor to explore its environment and to learn about the environment. Because if we would always choose the best action, it would never learn how much it could achieve by choosing an action that is worse than that. So basically what it boils down to, we will either choose the best one, or for a random amount we will choose any action. Now let's look how this is implemented in code. The Q-learning itself is basically structured in a general way. So we have it templated as part of a system, which means that the Q-learning itself is independent of the system itself, which means that we could also have not the roombot, but I don't know, something else that we want to learn about. But it doesn't need to be any roombot, it just needs to be a specific system, and the system needs to have states and actions, and that's basically it. And those states and actions, they need to be hashable because we will store them later on in an unordered map or an unordered set, respectively. The update itself is structured in two ways. So first, we act, which means that we ask our actor what is the best move. Then we will actually do this move. And after that, we will learn about how good this move really was. Now we have already looked into how Q-learning chooses its action, and that is also what we will do here in the act function. So this is called an epsilon greedy policy, which means that for a random amount of time, which is based on the explore rate, so 0 means that we will always choose the best option, and 100% means that we will always choose a random option, and everything in between is just a mix of both. So either we look at what actions are possible in this particular state, and then we will just use random distribution and choose this as an action. So we just sample a random distribution of all of the actions and use one output of this random distribution and put it as an action. Or we choose the best action that is currently available to us, which means that we again query for all of the possible actions in that state, and we use the action that has the highest current Q value of this state. And then we just choose this action. And that's already it. This is already how our actor will choose its action. Now let's have a look at the learning. The learning itself is a little bit more complex, but don't be afraid, it's not too much. So usually we had an old state, and in this old state we decided to take some action, which in our case was we wanted to go down. So we end up in a new state, and here for instance we see that this new state now ends up with the robot being here and another clean tile. And with this new state also comes the possibility for probably up to 4 new actions, depending on where in the map we actually are. Now what is important is that based on how good this new state is, we can update the action that we have chosen previously. So it means that if we get here a good reward in a new state, this means that this action here will be probably improved. If we get a bad reward in this new state, this means that this action here will probably be decrease in value. The equation how to update this is called the so-called Bellman equation, and we will have a look at it, how it will look like in code. This is the learning functionality, and here we just gather the reward of our new state. So we ask how good is this state compared to our previous state, and then we will use we will query for the best possible option of the current state. So if we look here, we will say that given our best option, might it be Q up, Q down, Q left, Q right, this is basically the expected reward of new state. Because if we would always follow the best option, we would end up with this particular reward. This is basically here, so we go through all the actions and we use the maximum expected reward, the maximum Q value of this particular action. Afterwards, we update from our previous state the Q value based on this delta, and this delta is now computed using the so-called Bellman equation, which is that we take the current reward, then a discount rate times the future reward minus the current Q value, and all of this times this particular learning rate. The learning rate and the discount rate, they are some high-level tuning parameters of this learning algorithm. So in order to make it learn faster, but probably not as robust, or make it learn slower, but probably more robust. And then we will update the Q value of our last action that we have chosen in our previous state. That's already it about the learning part of this algorithm. And this is now a general Q learning class which you could employ to any type of system. So it doesn't need to be a roombot, it just needs to be a system which has actions and states. And if you have designed a system which has action and states, this Q learning algorithm can be used to actually do this. The last part of the code is the GUI code or the surrounding driver code, which holds all of our stuff together. The first thing that we want to have here is on a very, very high level, define which map we are operating in. And we have here a map that is 6 times 6, and this is the map which holds all of the cells which are occupied and not. And you see here it has the same structure as later on here in the GUI, this part of our robot. This map will be later on used in our implementation of the learning algorithm, which is here represented by the Q learning member. So we have Q learning, we have the roombot, and we have the map for this particular Q learning stuff. The Q learning itself here is now updated in the GUI loop, which means that here in our Q learning, we will basically have two states. We will have a learning state and we have a show run. So the show run will basically do all of the update of the map, to basically show how a sample run would look like, and the learning state will in the background run a lot of updates to actually make the robot learn, and it will run a lot of different episodes. So we will start with the Q learning and we will have two conditions. So either all of the tiles are clean or we have run out of moves, and we have here selected the certain threshold of moves up until when we will reset the system. Then we will update the Q learning, and after that we will just log how many tiles we made clean and how many moves we actually made. One important thing to note is that with each iteration we will reduce our explore rate. This is something that is called an exponential decay, which means that at the beginning the robot will move out and it will try a lot of different actions to improve its knowledge about the system. And later on, it will narrow down its choices to the best options that are available. So this is basically a good indication, and we will also later log this explore rate, how many random actions the robot actually takes. And it is important that we use this sort of exponential decay to make the learning a little bit more robust. Then we will log all of these things and we will later plot it here in the graph. So we will have here the average clean tiles per run, the average moves made, and also how our current explore rate, so how much randomness does the robot have during choosing of his actions. And the second GUI state is this show run, which basically shows for one of the runs, because here we're running thousands of different runs, and then for one of the runs we will plot it into this update function here on the right side to show one of the runs after a certain number. Then it will go back, learn in the background, and after learning in the background it will show how the next run would look like. So yeah, that's basically already the complete system. Here this is then the GUI of the system. The GUI of the system consists of two parts. The left part is the statistics. Here I'm using implot, and implot I'm just plotting specific statistics that I have shown: the average clean tiles, the average moves made, and also the explore rate. And on the other side we're plotting this roombot run, And here, given the state, we will just color the rectangles in a different way. So we have here a specific function to plot rectangles, and if the tile is clean, then we will plot it in a green color, and if the tile is dirty, then we will plot it here in this red color. And if it is not even present in the map, then we will plot it in the background color to not have it on our visualization. That's basically all it. So we are able to plot the state, we're able to learn, we are able to run it all in the background, and let's start it. In the meter parameters, we can still define a little bit of things. So for instance, how many moves is the robot allowed to make? How many episodes should it train in the background until it shows again? And also whether it should start with some initial training or not. And then also we have some timings for the GUI until when should the GUI update and change the state and so on. So let's try it out and run it and watch how the robot improves. So here, after compiling, we start with the first episode, and the first episode, we see here the robot is more or less driving randomly around. And now it goes to the background, and it has then afterwards executed 20,000 different runs in the background and learned from all those runs while updating its policy based on the Q-learning algorithm. And then we see how our values change over time. So for instance, we started here with only 15 tiles clean on average for each of these runs. And we see that it slowly but steadily improves, which means that our algorithm is learning. Also, because of our exponential decay, it means that at the beginning we start with nearly 100% random moves to explore the environment, and then it goes slowly down, and for instance the last learning started with something like 90% random moves, and this randomness slowly but steadily decreases over time. And here we see that the average clean tiles for the learning goes up. So we see we started with the 15, and now we already have more or less something above 17 clean tiles per run. As soon as the clean tiles will probably reach basically all of the tiles, we will also see that the average moves made will go down. So right now it will always do all of the 100 moves because it's not able to clean the whole map. But after some time, and you see that it already starts, it will be able to clean the whole map because it has learned a little bit and because the randomness decreases. And if it cleans the whole map, then it will need less moves to do so. And we will see that after a certain while also the average moves go down until it goes to the least moves possible. And the least moves possible will always depend obviously on the map that you give the robot, and whatever best path then the robot finds to actually clean this. So while the robot is here a little bit learning, we can also look a little bit at the parameters that we have to alter a little bit of the learning process. Because one of the things that we have is in our Q-learning this particular explore decay rate, which basically means that how fast does our explore rate decrease. And using this, we are able to make our algorithm learn faster, but probably a little bit less robust. Then what is also important is our reward function. We have implemented this in our state, and here we have a specific reward function. And this is really crucial for successful learning of your robot. Because if the reward is not really reflecting what you want, it can be that your robot is also not really learning what you want. So for instance, here we just learn based on a change of the tiles, not on the total tiles that are clean, because this would skew the robot in a wrong direction. And also it's impossible that we give a small negative reward for each move that we do, because using this, it will encourage the actor to actually also search for the path that is the most efficient in cleaning the apartment, right? So because if we don't do this, then it will probably end up with also cleaning everything, but not in the most efficient way. What is also useful as parameters are the learning rate and the discount rate. These are basically also meta parameters of Q-learning. So learning rate means that how much of the information that the robot has should it update. So how fast is it learning from the information that it gets? If it is learning fast, it may also become unstable. If it's learning slow, then usually it's more stable. And the 1 would mean that it's learning everything, and the 0 would mean that it's learning nothing. The discount rate is useful if you work with systems that are not 100% predictable and have a certain probability built in, where you don't know when in which state you will end up. And this discount rate basically means how much of your future reward, so how far are you looking in the future. If you have a small discount rate, this means that you're basically only looking very short into the future. And if you have a high discount rate, this means that you're also taking into consideration rewards that happen far away in the future. And in our case, this is what we want. So we have a discount rate which is close to 1, because we also want to increase the rewards that we get in the future. So yeah, let's have a look at how the learning is doing here in the background. And we see the robot has already gotten a lot better than before. We see that the average clean tiles has approached its maximum. So it's always cleaning all of the tiles. Right now it's not cleaning it in the most efficient way, but we also see that the average amount of moves has already decreased quite a significant amount. And if we now would let it run for more time, we would end up with a robot, as I showed at the beginning, which is cleaning all of the tiles in a perfect way. So that's it from today. I hope you have learned something. You have learned something about reinforcement learning or C++. So please put a comment below what you liked best. If you want that my apartment is a little bit bigger than before, please also hit subscribe. And if you want to keep watching, I think here is the right video for you. Thanks for watching, and as always, get the code from GitHub, download it, modify it, give it your own map, give it your own system even. Put below if you have something really cool that you want to share, and as always, enjoy coding.